coming to the experiment, I told you I'll just concentrate. I'll not talk anything more about experiment number 1 or experiment 3. I'll just speak about experiment number 2. We have to use 741 op-amp, and we need to design relaxation oscillator, right? Let me go to the circuit first. So what is a relaxation oscillator? So you have a theoretical part in ADE that you come across. So here is the first experiment you have. Relaxation oscillator, that is we need to get a rectangular waveform for a given frequency. In fact, your experiment has been made very easy, saying that it is fixed to 1 kilohertz in the syllabus copy. But in the examination, if they ask you for different relax for the frequency 800 kilohertz or 2 kilohertz, you should be able to design this 741 op-amp. Clear? Fine. So once again repeat. So they have specifically given the relaxation oscillator for a given frequency. Okay. So there was a confusion regarding joining time at 2:45 by mistake. Then I thought of starting the session 2:30. As I said, I don't need any sort of attendance as of now. I'll tell you when to give it because I need to submit this chat file to Nandish sir. Okay. So let me continue. Here is the background. So background, you have seen this background in the video. What is relaxation oscillator? What is non-sinusoidal? And what all the values it uses? What all the different types of resistors the circuit consists of? It consists of a resistor R1, R2, and a final wire Ru. And this is the standard formula to calculate the value of T time period. F is called a frequency, right? So we need to calculate the inverting feedback resistor called R, and we have a separate R1 and R2, and always we keep for our assumption R1 equals to R2. Okay. So where C is a capacitor, and this theoretical part you need to go through, and you come across even in theory, that is a op-amp circuit, and in that it is a relaxation oscillator. By using, you have many experiments on op-amp, but for our lab we use 741 op-amp for relaxation oscillator. Even we have one more experiment called schematic that you come across in the theory. So but we don't have a lab session for the schematic. Okay, here is the circuit diagram that you use 741 op-amp, right? So before that, this is a fixed circuit we have, right? Always 2 is being connected to the capacitor C. It is 0.01 microfarad. Fine. And we have a resistor R1, R2, R1 and R2, right? And this is the waveform that we need to get. This is called a single time period. Starting from here to here, how do you measure? Basically, this starts from here, it reaches the peak and drops over here. So this complete cycle, you could see my pointer, mouse pointer. So it has reached the peak, that is a 50%, right? Once it reaches, it again goes back, comes down. So till here to here, the complete is called a time period. For the complete time period, we need to calculate this complete time period, and from that we need to calculate the frequency. That is what the experiment all about is. So you know the circuit, all of you. So here is the circuit. Here is the complete circuit, right? What all the calculations you have? As I said, these are all the standard formula. We have to remember 2RC natural log of 1 plus beta by 1 minus beta. This could be written as logarithm natural log of 3. So natural log of 3 is natural log of 3 is 1.098. Okay. So we have formula T equals to 2RC logarithm of 3. So 2 is number, R we have to calculate, capacitor we have to consider 0.101 microfarad and treating R1 and R2. So 2.196 into R into C. Okay, this is the equation 1. So given the frequency given is 1 kilohertz. I said we can change the frequency. If I say today I will go with the two frequency, one is a 1 kilohertz and one is a 800 kilohertz. So if it is a 100 kilohertz frequency, you need to calculate time period t equals to 1 by f. So 1 by 1 kilohertz is equal to 1 millisecond, right? Time period is 1 millisecond. You know what you have found the t value. Treating C equals to 0.1 microfarad and R1 R2 equals to 1 kilo ohm. We apply this, substitute these values, that is into this formula, 2.196 into R into C, C 0.1 microfarad, T you have calculated 1 millisecond, you calculate the value of 4.55. So using these value, you need to build up this circuit. R1 R2 is 1 microfarad, sorry, 1 kilo ohm, 1 kilo ohm, 0.01, 0.1 microfarad. You have to calculate the R value using this formula. This is a standard formula we have. So how did you get log of 3? So in fact, this whole value theoretically, when you come across, this is treated as 2RC log 1 plus beta by 1 minus beta as log the natural log of 3. Okay, it is treated as natural log of 3. Clear? Let us move. So given the frequency 1 kilohertz, calculate the time frequency. All of you have this lab manual. You can proceed further with this. So you calculate the value of R. So, but this is a theoretical value 4.55. We don't have a practical value 4.5 exactly. So what do we do is, what do we do? So we do select a nearby value 4.55. So that is equal to 4.7 kilo ohm. Fine. So we have 1 kilo ohm, 1 kilogram. This we have given it, and we have selected 0.1 microfarad, the value of capacitor. This is a first experiment that we have to do. Similarly, if I ask you calculate for the frequency f equals to 800 kilohertz, so first you have to calculate first the time period. Time period is nothing but 1 by f, that is 1 by 800 into equals to 1.25 milliseconds. Same thing, treating R1 R2 equals to 1 kilo ohm and C equals to 0.1 microfarad. We are going to calculate the value of R. So value of R is 5.69. Clear? So theoretically it is 5.6. We have exactly the near value called 5.6 practically available, so we can use it, right? In simulation it is not a problem, but in the case of practically, when you do the experiment, there is a problem. If the third, if they change the frequency, this is what I said, for your syllabus he has given you exactly 1 kilohertz. That doesn't mean that examiner may not ask you to change the frequency. He may ask 800 kilohertz or 2 kilohertz, right, or 3 kilohertz. Based on that, you need to find what is the final value of R, treating R1 equals to R2 equals to 1 kilo ohm and C equals to 0.1 microfarad, right? Clear? So similarly, see f equals to 2 kilohertz, treating R1 R2. So you have to calculate this. This is a practical example for you that you need to do it. Fine. So hopefully the people who are really hearing the session have understood the calculations. No uh, confusion in terms of calculations of calculating the value R. You need to calculate the value of R given the value of R1 and R2 and C equals to 0.1 microfarad, along with frequency is given. Remember, frequency is given to you, right? So this frequency, for a given frequency means for your experiment he has given 1 kilohertz. We will give, the examiner will give the frequency. For the frequency equals to 1 kilo, I may say 800, I may say 2 kilohertz. Then you have to calculate the time period. Based on this time period, you need to use this formula. This is a standard formula, remember. You need to calculate final R. How do you calculate? You calculate T based on the given frequency F. So you substitute the value of C equals to 0.01 microfarad, right? So based on that, you get the final value of R. And always we do treat R1 equals to R2. Fine. Similarly, now let us move to the next concept. See, first, before that, how do you write the results? So to write the results, I have given theoretical value 1 millisecond. Okay, for example, I have given the frequency equals to 1. So you calculated theoretically 1 millisecond. Similarly, you calculate 1 millisecond based on the value R1, R2 equals to, you calculate practically CRO. This 5.3 is being measured in CRO. Remember, 5.3 into 0.2, these are all the calculations in CRO. You are quite lucky as of now that you don't have a physical experiment. You have only the direct values to be calculated in simulation, that is in multisim. Similarly, practically, once you find T 1 by T equals to frequency, you match 0.94 kilohertz. You match this frequency with the theoretical frequency. See, it is nearby almost, right? This is a practical value. Similarly, we have simulation part. So in simulation, what do you do? In simulation, what do we do is, this is a table. This is a table for simulation. See, theoretically, you calculated it. Practically, you have calculated frequency. Though just now I have shown you the previous diagram. So in the simulation, you have to get this value 1.1 millisecond in simulation for T. The value of T has to be obtained. So this, let us move to the fast. Let us move to the multisim as of now. You know how to switch over to the multisim. Clear, all of you? Theoretically, let us not go in depth. So multisim, here is an application. Click on multisim icon where we have an application part, right? So multisim will open. You know the interface of a multisim, right? You know the interface of a multisim. This circuit has to be drawn. R1, R2 equals to 1 kilohertz. And what is the final value? 4.55 will take 4.7. Okay, practical value 4.7. For the frequency f equals to 1 kilohertz. Fine. So you need to design this. So now you can see here. So you have, now you can able to see. Now first I need op amp. So for op amp, you can focus over here. You have ANA, analog. Click on this. When you click on this, I'm going slow. Okay. Those people are not following, just ANA, analog. Here you have, you can see, you focus on this, you see op amp virtual. But we'll go with the op amp non-virtual. So I'll click on this op amp. When I click on this op amp, so you get here various component name list with respect to op amp. So I need 7.4 op amp. Click OK. When you click OK, so you get an op amp. And here one thing that you need to remember, the pin numbers of the op amp, this is 3, this is 2, and this pin number is 7. Remember, this pin number is 7. There is some problem with the software that it has been extended. This pin number is 1, this pin number is 5, this pin number is 6. 6 is okay, but pin number 5 is here. This middle one is pin number 7, leftmost is pin number 7. Fine. Now let us design the circuit. See the circuit, what you have to do, you know the value of R1, R2. R1 is 1 kilo ohm, R2 is 1 kilo ohm. Fine. And what is the value of R? R is 4.7 kilo ohm. Remember that, 4.7 kilo ohm. Now, so in between 3 and 6, you have to connect a resistor R1 with 1 kilo ohm, right? From 3 to R2, you have to connect with the 1 kilo ohm. Fine. So one more thing, what you have to do, you have to connect pin number 7 to DC voltage plus voltage, and pin number 4 to minus 12 volt DC voltage. So pin number 7 and 4. Let us finish that first. Okay, I'll close this. Now see here, where do you find the sources? In the sources, you have a DC voltage. See, this is a DC voltage. This is a fixed DC voltage. I'll take 2 of it, right? I'll click over here, right? Again, I'll click this. I'll drop over here. Pin number 7 has to be connected to the positive voltage of the positive plus voltage, right? Pin number 4 has to be connected to the negative of the DC voltage. So which is pin number 7? This is leftmost is the pin number 7. So it has to be connected to the positive. So I'll connect it to the positive. This is a positive terminal of the DC voltage. Remember, upside. This downside is a negative voltage. Similarly, pin number 4 has to be connected to the negative side of the DC voltage, right? It has to be connected to the negative side of the DC voltage. See, I connected. Just drop it. Now, the opposite side has to be grounded. Remember, it has to be grounded. I'll ground this. Fine. Again, take one more ground, click over here and connect this to the, okay. Fine. See, 7, pin number 7. This is a pin number 7. So as I said, naming conventions still you don't have a confusion. 7 is connected to the positive voltage. Next is grounded. So pin number 4 is to be connected to the negative DC voltage, and other part has to be connected to the ground. This part is over, right? Plus 12 volt, minus 12. Pin number 7, pin number 7, pin number 4. Now what else you need to do first? So in between pin number 3 and 6, connect resistors R1, right? In between 3 and 6, take a resistor. Always we take the virtual resistors. We take a virtual resistor virtual, click here, drop here. We need 3 resistors. Again, I'll click, take one more resistor, I'll drop here. I'll take one more resistor, I'll drop here. So what are the resistors in between 3 and 6? 1 kilo ohm. Again from 3, 1 kilo ohm, right? So what R has to be connected in between 2 and 6. So all is 4 point, R is 4.7 kilo ohm, right? So I'll change this, modify the value. It is 1 kilo ohm as it is. This is 1 kilo ohm as it is. And this is 4.7 kilo ohm, right? 4.7 kilo ohm. Now in between 3 and 6, you can do it vertical flip or horizontal vertical, as of somehow you can clockwise, you can connect it, right? Pin number 3 to 6, you connect with the, see, pin number 3 6 has been connected with 1 kilo ohm, clear? Pin number 3 to 6 has been connected with 1 kilo ohm. Somehow you have to manage to connect it. And 3 to 3 again has to be connected to resistor R2, and it has to be grounded. So I'll take this resistor over here, connect this part again here only, right? Another part has to be, take a ground connection, ground it, ground. See, fine. So what is the next step? Again, in between 2 and 6, in between 2 and 6, we have to connect a resistor with 4.7 kilo ohm. And with 2 and 6, so you have 4.7 kilo ohm over here. So take a resistor, connected. So another part connected. Now compare the circuit. In between 2 and 6, R resistor is there. In between 3 and 6, R resistor is there. Again from 3, one more resistor. See, from 3 to 1 kilo ohm, 3 to 6, 1 kilo ohm, 2 to 6, 4.7 kilo ohm. Whereas pin number 4 connected to negative plus 12 voltage, positive 12 voltage. Other part is been grounded. Very simple to remember, right? Once you draw the op amp, you find it easy. Now you take a capacitor. Another part of art has to be grounded, right? And you take a capacitor. From pin number 2, you have to connect and ground, right? From pin number 2, you have to connect and ground. So take a, click here, you have a virtual capacitor, take virtual both for resistor and this one, you take virtual, okay? But it is not 1 microfarad, it is 0.1 microfarad. Remember, you do the mistake while doing the experiment. You keep only 1 microfarad, you don't change it, then you will have a error. Fine. So this has to be connected at pin number 2. So I'll drop over here, it has to be connected at pin number 2. So one part you can flip if you want. Now one, no polarity, positive or negative as such. One is connected to the pin number 2, another has to be grounded, another part has to be grounded. Fine. Fine, no confusion. Hope all are following the experiment. So next what you have to do, C has to be grounded. Now we have to connect to the CRO. How do you connect it to CRO? So you have an option over here, I shown you. So here oscilloscope is there, no, this is CRO. No other thing will be used, no other things will be used. So you have a CRO. So one part has to be connected. So CRO pin number 6 output, input has to be connected to the pin number 2, right? Where you have pin number 2, you take this terminal of CRO, okay? So somehow you can take, you connected to the pin number 2. I connected. So another, take the terminal pin number 6. Fine. So take one ground connection and connect it to the ground. So now our circuit is over. Just verify whether all the components are present or not. See, 3 to 6 connected with 1 kilo ohm, right? 2 to 6 connected with the 4.7 kilo ohm. Similarly, pin number 3 with 1 kilo ohm grounded at another side. Pin number 2 connected to the capacitor 0.1 microfarad. Remember, you need to modify it. When you drag, you'll get 1 microfarad. This is virtual, this is virtual, this is virtual. Whereas op-amp is not virtual. You go to the ANA analog. Here you have a, when you click there, you get 741 as such. Now your circuit is over. Now what you have to do, you just have to run the simulation. And remember, this 4 has to be connected to the negative voltage, and this has to be connected to the positive voltage. And another, the other part of it has to be grounded. Fine. So let us run the simulation. The simulation is running now. You double click the CRO. Now you could see some sort of simulation. When you run the simulation, you just change the scale, okay? See, I have changed the scale to 500 microsecond. So I'll just pause. I'll pause. Now I'll move this cursor over here. Now you have the meniscus. You can focus the meniscus. See here, 1 and 2, you have 1. I'll focus here. All of you see, how do I measure? Measuring is too important. 2, I'll focus here. How did I focus? One complete time period cycle. See, 1. So imagine where does the waveform begins, or else you can focus here also. If you have again confusion, okay, you can take this or this complete waveform where it has begun, okay, or else see here you can focus. If you have still confusion, I have focused here, to I have focused over at the end of it. Now you have to measure. In simulation, it is very easy to measure. That is, T2 minus T1 gives the time period directly. T1 minus T2. This is T1, this is T2. Okay. So between, sorry, T2 and T1. T2 minus T1. T2 166.7 millisecond. So in between T2 minus T1, you could measure 1.1 millisecond. So this has to be noted. This complete time period. This is a complete time period. Clear? 1 to 1. So this gives the 1.1 millisecond. Now come to the readings. So all these things you have done theoretically, 1 kilohertz, 1 millisecond. Practically this you are going to do it only on CRO in the lab. As of now, you need not to worry. Coming to the simulation. In the simulation, what you have found? You have found the value of T. From where you have found T2 minus T1 is 1.1 millisecond. Same you have got it. See, 1.1 millisecond. Now calculating frequency from that, what do? You just reverse it, no? F equals to 1 by T. 1 by 1.1 millisecond. Remember, 1 by 1.1 millisecond gives 0.909 kilohertz, right? So we have got frequency equals to 0.909 kilohertz. It is almost nothing but a 1 kilohertz only. So we match this simulation with this theoretically 1 kilohertz, and also we match this simulation with this practically 0.943. Practically we have got 943 kilohertz. How did you calculate it? That is reverse of 1.06. Again, reverse of 1.1 milliseconds. What you have got in the simulation, the same thing we have found it practically almost the same, right? This table you have to write in the exam. For your exam, if you do with a simulation, if you are not using this here, these values are not needed, but these table has to be plotted. Similarly, I will just modify the same simulation part. Now I will close the simulation. I'll off this button so that the simulation is closed. Now coming to the concept, if the second case F equals to 800, you do certain calculations, right? Treating R1, R2 equals to 1 kilo, 0.1 microfarad, treating the same formula, T equals to RC, natural log of 3, 1.098 it is. You calculate the value of R. R value is 5.6 kilo ohm. Now you see what is 5.6 kilo ohm. So just what you have to do in this simulation part, all of you just focus here. I'm just modifying to the same experiment the resistor value, treating everything is same. 4.7, I'll just modify it to 5.6 kilo ohm. 5.6 kilo. Why I have modified? I am doing case 2, which is equals to, for the frequency 8 kilohertz, I've calculated the value. All of you. For a frequency 800 kilohertz, I calculate the theoretical value, that is 1.25. Based on that, I calculate the resistor value, right? Based on the resistor value. What was the resistor value? See here, 5.6 kilo ohm. No? So I inputted 5.6 kilo ohm. Now I'll run the simulation. And what is the answer that you have to get? You have to get the answer as the frequency you should find 800 kilohertz. Okay. That is 1 kilohertz. We have got nearby to 0.9 and you should get a 800 kilohertz. Okay. Now you run the simulation. Now you stop the simulation, pause the simulation. Now you measure what is the difference between T1 and T2. One complete time period is being measured. T2 minus T1 is 1.3 millisecond, right? So 1.3 millisecond. All of you, are you able to see what is this? 1.3 millisecond. We have found T2 minus T1 is 1.3 millisecond. This is for the second case where you use a frequency equals to 8 kilohertz. So how did you do? This I have given you the value 800 kilohertz. Based on this value, what you have to do? You have to calculate the time period. What is time period? 1 by f, 1.25 millisecond. You got it, right? So in the simulation, you got exactly 3 millisecond. Is it or not? So based on these values, theoretically, you found the values and you got this resistor value, that is 5.6 kilo ohm, right? Is it or not? Then what we did? Practically we have not done. See, theoretically 1.25 you got, no? Same thing it is being, I'm showing it. I'm stressing on this value 1.25. So in the simulation, what did you got? In the simulation you got 1.3. I'm just comparing the theoretical value with the simulation value 1.25, 1.3. So how did you get the frequency? Reverse of 1.3. So I'm just reversing this 1.3. When you reverse this 1.3, 1 divided by 1.3 millisecond, you have to consider 10 to the power 3, remember? So you get 0.769 kilohertz. It is almost equals to the 800 kilohertz, right? 800 kilohertz. When you convert it, you get it is a 800 kilohertz. So you have found the frequency. Similarly, you can do for many given frequency 2 kilohertz. You have to find the value of R and you have to get. So ultimate objective is that from the experiment you should get the reverse answer. You should get the reverse answer. Theoretically given value I gave 1 kilohertz. You calculate time period. Practically you have to calculate practically also. Maybe no, I have no, I cannot show you the CRO values. Practically final value what he has got, time period equals to 1.0 millisecond. On reversing, we have got 0.9. All of you can give the attendance in the chat session as of now. So meanwhile with the explanation, all of you can, those who have not given the attendance in the chat session can give. Yeah, clear all of you. Simulation have shown you how did you get these values. So this has to be obtained. This has to be obtained. And on reverse of 1 by 1.1 millisecond, you get 0.9. This you get. Similarly, 1.3. 1 divided by 1.3 millisecond. So you get this. I compare these value, point frequency, with my theoretical frequency. And also I compare the same value with the practical. Practically anyway, you are not doing with the CRO. So this value with the, see, almost the frequency is being matched, and the time period is also almost the same, 1.3. Here it is 1 point, right? So that is the way how you do the experiment. Yes.